Okay, well, welcome back, everyone. Actually, maybe before I start, is there any question about what I said yesterday? Okay, you all solved all of the exercises and everything works. Great. Okay, so let me start again with the theorem I ended with last time, this coordinates, because I want to tell you a tiny bit about how you see that this is actually a bijection. So these were the Fenchel-Nielsen coordinates. So we had these two collection of curves. P was a Pansy composition, and Q was this family of, say, transverse curves. I mean, with the properties of yesterday. And then we knew that there was a bijection between Teichmüller space of a surface of genus G and R positives times R to the power 3G minus 3, where here the map was, I have my Pansy composition, that's the alpha i's, and to each surface here, I associate the length of the curves and the twist parameters. Okay, and there was this funny way of constructing the twists, which essentially is supposed to encode the way you glue. So it's a bijection. So these twists are supposed to encode the way you glue pairs of ends. Now, so essentially I told you yesterday how to construct this map and to give you an idea of why this is, why you can go back. So how can you start with a set of parameters? How can you construct a curve? We just want to start with one remark in hyperbolic geometry. Mark fact. In H2, if I take any three lengths, and it's three positive numbers, there exists a unique optoisometry. Hyperbolic, so rectangle hexagon, which is determined by these three lengths, meaning that the lengths of alternating sides are x, y, and z. So with alternating sides, of length x, y, and z, so that the drawing to have in mind is something like this, where you have only right angles, and then you know that this is length x, this is length y, and this is length z. So if I give you these three numbers, there's exists a unique hexagon. It's something that one can show. It's not hard, but it takes, but it might be a little tedious. So what is the idea now? If I take two such things, I can glue them together. So I don't glue them together entirely. I glue only the sides that have the length of that I don't know. I mean, that I actually know, but the length that I have not given a name of. Okay, so I have one of those, x, y, and z, and I take another copy of exactly the same, x, y, and z, and I can glue sides by isometries. So this one with this one, with this one, and this one, and this one, and this one. So what I get topologically is a pair of pans. With these three lengths here that are actually geodesics orthogonal to the boundary. So this we get a hyperbolic pair of pans, meaning a pair of pans with a hyperbolic structure. And we know what the lengths are of the three boundary components. The boundary components of length 2x, 2y, and 2z. So this tells me that every time that I have three lengths, I can construct a hyperbolic pair of pans with these three boundary lengths. And this is going to be unique because if I have another pair of pans with the same lengths, I can cut along the orthogonals, the ones that here have colors. I get two identical, by symmetry, hyperbolic hexagons with the lengths that are half the length of the boundary, and those are unique. So this tells me that if I have a topological pan composition and I fix the length of the curves, I can realize each pair of pans as a hyperbolic pair of pans with the correct length, and then the twist is the one that tells me how to glue. So the point is, if I have Li and Ti, so I get I can construct pairs of pans with the right boundary lengths and use the Ti to know how to glue them. And so I get a hyperbolic surface, I get a surface in Teichmüller space. Here everything is very imprecise because I haven't told you exactly how, with the twist, you can construct the thing. And then what I'm saying here, I can construct any surface like that. You also need to construct the marking, but well, I hope it convinces you that that something like this could work, and that this can actually be a bijection. Now, so far when I talked about Teichmüller space, this was just a set, and there's many ways to topologize it, and I am just gonna maybe slightly cheat, and I'm gonna say this is the way to topologize it. So you can use this bijection to give a topology on Teichmüller space. So now, use this bijection to construct a topology, or to give a topology on Teichmüller space. So, of course, here there's lots of stuff that's hidden. There's not a unique Pan's decomposition. There's many coordinates. So what I'm hiding here is the fact that if you take different Pan's decomposition, different coordinates, you always get the same topology. I don't know what happened. Okay. The point is, there's also many other ways of constructing a topology. and they all agree with this topology. And here, actually, it's very important to assume that your surface is of finite type, otherwise everything gets infinitely more complicated. Different metrics, different topologies. You get all sorts of different topologies. The space can be connected, not connected, depending on what you choose. So here it's really important to have the finite type. So the thing I wanted to mention is, in particular, so we have another way of giving a topology now, looking at the fact that we had realized Teichmüller space is a connected component of a space of representations. There is a topology, and what I'm saying is that maybe it's a theorem, is that Teichmüller space like this is homeomorphic. Now it's more than a bijection to the corresponding connected component, thanks Sami, of the space discrete and faithful representations of PSL2R. Here we spoke about a topology here. We can just look, for instance, convergence on a set of generators for the fundamental group. So this as a natural topology, and what I'm saying here is that the two topologies are the same. So for instance, once you showed, if you can show that, you show that the topology up there does not depend on the choice of Pan's decomposition, because this one does not depend on anything. Okay. Now I wanted to mention something which is a natural action on Teichmüller space. So I mentioned, to me, one reason to look at Teichmüller space is because it's a universal cover of moduli space. So I told you that if I want to do that, I need to try to understand moduli space. I can try to understand its universal cover, but then I also need to understand its fundamental group. And this is the action I'm going to talk about. So here we have, given a surface, we have a group which is called the mapping class group. Which can be defined in many ways. I'm going to think of it as the group of orientation preserving homeomorphism of the surface up to homotopy. And here you could choose isotopy, you could choose these to be diffeomorphisms, and then in the case in which the surface is finite type, you can also choose, you can say more, you can choose quasi-conformal maps. We'll mention this quickly later. Okay, so this is a group that's associated to a surface, and this acts on Teichmüller space by changing the marking. So if I take the class, well, I don't know, of a homeomorphism there, and I take the class of something here, so this is something that's a homeomorphism of the surface. Is, I remind you, is a map from the surface S to X. So I can pre-compose with H inverse. Otherwise, I think things don't go correctly, but this gives you a way of getting an action of mapping class of the mapping class group on Teichmüller space, and you can check that everything works. So all of these things are defined up to homotopy, which means that in practice there's up to homotopies that move around enough to make this not depend on the choice of representatives. And so we can quotient now Teichmüller space by the action of the mapping class group. And the fact, that's also going to be an exercise, is that if I quotient, I get moduli space. Okay, let me do it with G, because so far I've done that. So you can kind of see that what is happening here is that I am changing the marking. The marking was the thing that was distinguishing Teichmüller space from moduli space. In moduli space, I take two surfaces. If they are isometric, they form the same point. In Teichmüller space, I was remembering something more. And the action of the mapping class group is making me kill this extra piece of information that I had. So that's the intuition why this is true. And I wanted to mention, okay, first thing is, if you've never seen this group, I'm going to give you the example of one element in it, which seems like not a lot, but on the plus side, you can generate this group with elements of this form. And also, if you want to know more about the mapping class group, well, the Farber-Margolid book that I gave is all about that, or you can come and ask me afterwards. I can speak at length about it. So the element that I want to define is a Dane twist. And you define a Dane twist, you have a surface, and you pick a curve, a simple closed curve on it. Say, for instance, this one, an essential simple closed curve. Okay, so actually, this will depend on the homotopy class of that, and the Dane twist is usually denoted tau of A. Sometimes I'm gonna just write tau of alpha. So what does this thing do? This is very related to the twist that we had before. If you do a Dane twist about alpha, you cut the surface about alpha, you keep one side fixed, you twist the other one by 360 degrees, and you glue back. Concretely, or very explicitly, what you can do is that you can choose A, an annulus, which is a regular neighborhood of your curve. Of course, here again, there's many choices, and what one needs to do is to show that at the end, all of these choices give you the same thing. Now, this is an annulus, so I can identify it with a circle times 0, 1. And what I do, so the twist is going to do nothing outside this annulus, and it's going to do something very specific on the annulus. So let me say, there's clearly something. Okay. So I define a map that goes from the surface to the surface, so that x is sent to itself if x does not belong to the annulus, and on the annulus, the map sends, and now I need to check for the orientation of things. So I take a point x that I want to think of as an angle. For me, S1 is 0, 1, where I identify 0 and 1. T, and I can send it to theta minus t, t. So what is this doing? So for one thing, this is the identity if t is equal 1 or 0. So at least this map belongs to a homeomorphism of the circle, of the surface, which is good. And then what's happening is that, say I am here, here I do nothing, then I start increasing the time. Now, yeah, it's also, of course, it completely depends on the orientation. I'm going to draw one. Is there anything I can do for the, I don't know, for the microphone? What I want to say is that it does something like this. It does a tour, and it twists the thing around like that. So in the annulus, something that was just a straight line is turned into something that does the whole tour around it, which is why we call it a twist. Okay, and the other thing I wanted to say about this action is the fact that we have a properly discontinuous action. And so this in particular means that if I look at the quotient, it's not that bad as a topological space. It's not going to be a manifold, but it's going to be an orbifold. So kind of the next best thing. And somehow this also tells me that, I mean, there's really some hope into trying to understand the quotient by just looking at the universal cover and the action. The action is not super bad, so there's some hope of actually understanding something there. And to prove this, I want to use the black box, which is the Alexander method. Something that I guess is quite believable, if you think about it for a second, which is that there exists a finite set of, this was the homotopy classes of simple closed curves, such that if I have a mapping class and I know that it fixes all of these curves, then this map is actually the identity. Okay, so again, this you need to define the action. Everything is up to homotopy, so if I is the class of some map H and A is the class of some alpha, then phi of A is the class of H of alpha. So what this result is telling me is that some finite set of curves, so that if a homeomorphism sends all of them back to themselves, then it's homotopic to the identity. And maybe one way you could believe that is you take enough curves so that your surface is cut into disks. That's not really enough, but almost. Then if you know that all the curves are sent to themselves, in practice what you have is a map that's the same on these curves and that sent disks to disks. And on each disk, you can homotop each map to the identity. I mean, if you have two maps, if you have a map of the disk to itself that fixes the boundary, that is homotopic to the identity. It's just not super hard to write down. So that's kind of the idea behind this. But if we assume that, we can actually show this theorem. So I fix K in Teichmüller space some compact subset. And I fix also F as in the Alexander method. Now, what I can deduce is that there exists some constant so that for every point in Teichmüller space, if I look at the curves in F, the length is at most this constant. I mean, why? So one way of looking at it is if you take any, so the topology up there tells you in particular that length functions of curves in a Pan's decomposition are continuous functions. And the other thing you can think about is that if you have any curve, you can complete that to a Pan's decomposition. So this tells you that the length function of any simple closed curve is a continuous function, and we are on a compact, so there's an upper bound. Yes, in K. Thanks. No, otherwise it's very false. And now we look at f prime, which is a set of all curves that have length at most c for some element in K. So all the B and again here I need to, I wrote twice the same wrong thing. Excellent. Okay, so this is a set that certainly contains F. And what one can show is that this is finite. And this is essentially because this is finite on any surface. And then you are on a compact. If I look at the collection of curves such that the length of the curve is at most c for any constant c, this is finite. And I think this is an exercise. It's not super hard. Okay, and now if you take a phi in the mapping class group such that phi of k intersects k, so we need to show that this collection of phi is finite. That's the proper discontinuity. This is non-empty. Then what you can show is that this collection of curves is sent into this one. I mean, you're just changing the marking, so you have a collection of curves, so that you're remarking the curves that have length at most c. But now this is finite. So there's finitely many possibilities for the image of F. And now, so if you think about it slightly different, about this method slightly differently, this also tells you that if two mapping classes have the same images, so agree on this set F, then they need to be the same. You just apply this with one composed with the inverse of the other. And so this means that there's finitely many possibilities for phi that do this thing. So once I fix another way of stating the Alexander method is that once I fixed the images of the curves in F, my map is completely fixed, my mapping class is completely fixed, and since I have finitely many possibilities, this means that there's finitely many possibilities for phi. Okay. That makes sense? I guess if anything, this is the hardest. I guess it's easiest if you try to write it down, and if you are confused, you tell me. And maybe two remarks. One is that there's one case in which we understand all of this very well, which is again the case of the torus, which is if you look at the mapping class group of the torus, this is actually SL2Z, where you think of these as acting on the torus seen as the quotient of T2 mod Z2. So, well, this acts on R2 and preserves Z2. So this is, so you get one way of looking at this inside here, and then it's not very hard to show that these two are the same, but it goes certainly beyond the scope of what I'm doing here, so I'm not gonna do it. And the other thing is that in general, mapping class groups are much more complicated. Infinite, they are complicated, always infinite except in very few cases, like the sphere, it's trivial. The three-hole sphere is finite, but at least for a surface of genus at least 2, it's always an infinite group. And we know many things about them, but there's also plenty of questions that are still open. For instance, in the case of the torus, we know that this is a linear group. It's completely open whether this is true in for a generic surface. Okay. So the next thing I wanted to do was to talk a bit about, so far we've talked more about the topology. So the first, what is this set? How can we topologize it? But we can also give a geometry to this space. There's multiple metrics one can construct, and I'm going to talk about one, which is called the Teichmüller metric. And again, this will be another way of topologizing the space. We will give a metric, so one could use the induced topology, and something that I'm gonna just assume as a result is that this is the same, this topology is the same as the one that we just defined. Okay, so here we want to describe how close or far hyperbolic surfaces are between each other. So when we need to describe in a certain way, if we have a map between them, how much it distorts, how much the map distorts one surface into the other, and this is why we need to look at what are called quasi-conformal maps. So let's say I have x and y that are hyperbolic surfaces. And I take a map. Maybe phi is not ideal, but I'm going to follow this, otherwise I'm going to, which I can assume smooth. In practice it won't really be, but let's assume that it's as good as we want. So let's say a diffeomorphism between them. And I pick a point. So I'm going to first define something that tells me how much this map distorts the structure locally around X. And then I'm going to define something that's associated to the entire map by taking a supremum over all points. So what we define first is kx of phi, which is defined as follows. I take the derivative with respect to z plus the derivative. I mean, of course, here locally everything is in H2, so this, what I'm writing, makes sense. I have this. This is what is called the pointwise conformal dilatation. Quasi-conformal, sorry. At X. And then, yeah, so for the map, we define this to be the supremum over all points X in the surface of these ones. This is the global quasi-conformal dilatation. And so it might seem a bit of a funny thing the first time you look at it. One way of thinking about it is the following. So what does this measure? This measures how much, so the lack of conformality at a given point X. More precisely, it tells you how circles in the tangent space at X are distorted. Yep.
So what do we mean by the absolute value of phi z?
Yeah, you can think of all of that as being in. So locally, you're in the hyperbolic space, hyperbolic plane. So all of these, you need to do everything in charts. Yeah. Yeah. To me, all of my surfaces are orientable, yes. Yeah, I guess you need that. Yeah. Yeah. Yeah, in the end, in practice, what I'll do is everything with orientation preserving things. Everything is orientable. Everything preserves orientation. Any other? Okay, so these measures how phi stretches circles in the tangent space at a point. So if I have C here, which is a circle, then it's sent by a map phi like that. It's sent to an ellipse, not necessarily a circle anymore. And we know what the ratio of the major and minor axes are, and that's controlled by this. This is the length of the major axis divided by the one of the minor axes. Okay, so the main idea is so how do we want to describe the distance? We want to choose a class of maps. We want to choose something that tells us how much this map distorts, and one way of choosing that is to look at its quasi-conformal dilatation. This is a measurement of how much this map distorts the metric. And then you can define a distance between 2 points by trying to see how little I can distort to go from one to the other. So we can define the distance between xf and yh to be, this is Teichmüller's distance, it's the infimum over all phi as above, which are in the specific class. So always we need to restrict into, we always look at things that are in the homotopy class of this specific map of the quasi-conformal dilatation of the map. Sorry, there's a half and there's a log. Let me write it slightly bigger so that it's visible. The half is not very important, the log is. If we want this to be a distance, and then now one remark, hiding again some details, is that so a map phi is going to be conformal, so preserve angles, if and only if this constant is actually equal to 1. And one can show that this is equivalent to saying that this is biholomorphic. And we've seen that this implies, well, this is equivalent to being an orientation preserving hyperbolic isometry. So this tells us in particular, so when this is, so this infimum is 0. Let's assume for a moment that it's realized. Assuming it's realized, this distance is 0 when this log is 0, so when this is 1, so when there's a hyperbolic isometry in the correct class. And so this is exactly when the 2 points are the same. So the distance is 0 if and only if the 2 points in Teichmüller space are the same. So this is the part that's hardest to check. And then the other things one can check that actually this is a distance. The other parts are easier to check. You just need to essentially check that if you compose quasi-conformal maps, you have a control on the quasi-conformal dilatation of the composition. Well, that's essentially the only thing you need to do. So you get that this is a distance. And what I was saying is it's not obvious per se, but it's true. that the topology that this distance induces is exactly the same as the topology that I defined before. Okay, and what I would like to tell you in the last 40 minutes is a bit about the geometry of the space with this metric. And then hopefully maybe you have also a little bit of time to talk about the boundary of Teichmüller space. Okay, some results about the geometry of Teichmüller space with this distance. So maybe one comment in the exercises. One exercise is to show that this distance coincides with the hyperbolic distance in the case of the torus. So first maybe is a remark is that if S is actually the torus, dt is the hyperbolic distance. So this is recalling the fact that the Teichmüller space of a torus is the hyperbolic plane, at least as a set. And what this is telling me is that this is actually really isometric to the hyperbolic plane. So there we know quite a lot about its geometry. So we can So there, for instance, we know that it's a very nice negatively curved space. We know everything about its geodesics, and we can try to figure out how much of this carries on for higher genus surfaces. Okay, so the first thing I wanted to tell you is the fact that we can, and it's actually going to be needed if you want to prove this result. Well, at least it helps in proving that result. Is the fact that this distance, this infimum is actually realized by some map. And this is a result of Thurston. So the result is the following. First, I'm going to state it a bit vaguely, and then I'll introduce the thing to tell you what this results into in detail. So if I have 2 points in Teichmüller space, then there exists a unique map phi, which is called the Teichmüller map. Which realizes the infimum there. So that actually the distance can be computed in terms of the quasi-conformal dilatation of this specific map. Okay, and I want to tell you what these, how you find these Teichmüller maps. The point is there's a way of describing them, so you know that if you find a map that behaves in a certain way, you know it's going to be a Teichmüller map, and then you're going to be able to just compute the distance by looking at by computing its quasi-conformal dilatation. And to do that, I need to tell you what a holomorphic quadratic differential is. So I pick X, a Riemann surface. I'm going to take this viewpoint. We've already seen that if I have a hyperbolic surface, they have a naturally associated Riemann surface, so we can just look at this viewpoint. Then a holomorphic quadratic differential. I'm going to give first a definition that might not tell you anything, and then something concrete. what is that? Is a holomorphic section of the symmetric square of the holomorphic tangent bundle of X. Okay, so this is the bundle whose fiber over a point is the space of all C linear maps from the tangent space to C. So this might tell you something. If so, great. I have to say it does not speak to me, so I'm going to tell you what does that mean concretely. Concretely, these are things that in local coordinates have a very special form. So I take an atlas. Oh, sorry. For the surface, then Q is a collection phi alpha of Z alpha dZ alpha squared, which satisfies two properties. The first one is that the maps phi alpha are holomorphic and have finitely many zeros. And the second one is a condition to tell you how to glue the maps, which is that on overlapping charts, we have the following. We have the following condition. And the main thing that is going to interest us is the fact that once you have such a thing, you can change coordinates to make this this expression even simpler. So the fact is that given Q, a holomorphic quadratic differential, there exist coordinates we call natural coordinates associated to this. So that around a certain each point P in X, Q is of the form. So I don't need any map phi alpha, but I can just look at powers of Z, where Z squared, where K is some integer bigger or equal than 0. Okay, so in practice, you can, for one thing, you can reduce the charts in such a way that if there is a 0, it's only exactly your point, and then you know what's the behavior of the map around your point. And now, I think I need to go all the way up there. And now the point is that a Teichmüller map is a map that behaves well with respect to some holomorphic quadratic differential. And one way, I mean, if you want to prove the remarks that I put up there, what you can do is you can actually really construct a Teichmüller map between two tori by showing that, and showing that it's a Teichmüller map, you will do by finding a holomorphic quadratic differential. That's going to be pretty easy on the torus. And constructing a map that satisfies the right properties. And then you know that that is the one of which you need to compute the quasi-conformal dilatation, and then you can just show that that's the same as the hyperbolic distance, which is why I had at some point given you, at the very beginning, I had given you an explicit formula for the distance. There's many explicit formulas, and I think that's the one that's easiest to use to verify the statement up there. Okay, so let me tell you what a Teichmüller map is. So something is a Teichmüller map if there exists a holomorphic quadratic differential Qx differentials Qx on x and Qy on y. Now, once I have these holomorphic quadratic differentials, I have natural coordinates, and I wanted the Teichmüller map is of a nice form in terms of these natural coordinates. So I need this, and I need a k bigger than 1, some constant, so that two things happen. The first one is that f sends zeros of Qx. These are points that are, I mean, in this local coordinates thing is, these are points that are 0 for some phi alpha, and then you can check that if they are 0 for some phi alpha, they are 0 for any phi. And it sends those ones to the zeros of Qy. And then if P is not a 0, then in natural coordinates, the map has a very special form. So around P and its image point f of P, f is of the form x plus yz is sent to the square root of x times x plus I over the square root of k y. So it has a very explicit form, and then you can just check. So the point is, once you know that, you can actually compute the pointwise quasi-conformal dilatation. So k of f is going to be, what did I say? I said that it was bigger than 1, bigger or equal than 1. Actually, sorry, I wanted bigger than 0. And then, because I think sometimes you might want to get it less than 1, it's either k or 1 over k, depending on which one is bigger than 1. So this is if k is bigger or equal than 1, and this is otherwise. No matter what, this is something that needs to be bigger or equal than 1. Okay, so this might seem, I realize, once you see it like this, might seem a little confusing, and you might wonder why any of this is good. I unfortunately don't have the time to go into the details of this, but this allows people to do many more explicit computations and to understand much more the existence of such a map, and the fact that it behaves well allows you to know much more about what happens for this distance. So let me, now that I have written this down, I can actually tell you what Teichmüller theorem is, or what Thurston's theorem about the existence of the Teichmüller map is. And I guess the best way of convincing yourself that this might be useful is to try to show the remark up there. I mean, per se, I mean, it might be, if you think about it for a second, if you want to compute a distance and it's saying femum over a whole bunch of things, how do I even start? I mean, it's perfectly fine for trying to find bounds. It's not great if I actually want to compute a distance, and the fact that you know that there is a minimizer and it is exactly of this form is really helpful if you want to really compute distances instead of estimating them. Okay, so the theorem that I had stated up there, and that I'm now going to say more precisely, is as follows, is that one in each homotopy class of a homeomorphism between two hyperbolic surfaces there is a Teichmüller map and then the second thing is that if I have two maps which are homotopic, I suppose that F is K quasi-conformal. I haven't told you what that means. I'm realizing. Let me just add it there. So a map is K quasi-conformal. This supremum per se could be infinite. And a map is quasi-conformal if this supremum is finite, and the K is an upper bound on that. Let me say it here. And phi is K quasi-conformal if, let's say, K phi is equal to K or is bounded above by K. Usually we just need bounds. And then I have H, which is a quasi-conformal, is a Teichmüller map. Then actually the homeomorphism, then actually the KH is the best map in terms of quasi-conformal dilatation. So the quasi-conformal then K of F is at least the quasi-conformal dilatation of H, and we also know when we have equality. And this is if and only if I look at this. And this is the identity in the case that interests us. So this is in genus at least 2. Since you need the result also for the torus. In the torus, it's if and only if the map is conformal. Okay, so, well, okay, but let's forget for a second about the case of the torus. It's telling us that there exists a unique minimizer of this quasi-conformal dilatation in each homotopic class, and this is exactly the Teichmüller map. So we define a Teichmüller map as a map that has good properties in that way, and it turns out to be the map that does the right thing. Okay, so, okay, this was the first result. It's per se not yet the result about the geometry, but it tells you how to construct, for instance, geodesics between points in Teichmüller space. The second thing, I told you that in the case of the torus, Teichmüller space is the hyperbolic space, so it's negatively curved. And for a long time, people thought, well, for a long time, for a while, it was a theorem that there was negative curvature for Teichmüller space as well. And then actually they realized it was not true. This is a result of Maser and Wolf. Is that Teichmüller space of the surface with the Teichmüller metric is not Gromov hyperbolic. Okay, so this was defined yesterday. It's a notion on negative curvature. The idea was that we had these thin triangles. In particular, if you have negative curvature, you will be Gromov hyperbolic, but you don't need to talk about curvature to talk about Gromov hyperbolicity. And I can tell you, Minsky can tell you where this fails, what is this obstruction to hyperbolicity. So the lack of hyperbolicity is in the thin parts of Teichmüller space. And I'm going to tell you what these are. Well, I'm going to tell you the result of Minsky. That tells you how to find quasi-flats. So things that are almost flats in Teichmüller space. Once you have a flat, once you have something that's a Euclidean space of dimension at least 2, you're certainly not going to be Gromov hyperbolic. Triangles are really not thin in Euclidean space. So if you take epsilon, which is sufficiently small, and I pick some collection of curves, alpha 1 through alpha p, which are essential simple closed curves, pairwise disjoint and not homotopic. So this could be a single curve, and it could go up to a Pan's decomposition. Then I can look at I don't know why I chose this notation, but I'm going to stick with this. This is the thin part with respect to this. These are all the points in Teichmüller space where these curves are short. I want it strictly less than epsilon for every I. So this is often called, this is a thin part of Teichmüller space. It's a space where surfaces have a very short curve. Then what can we do? First of all, this is what I was telling. This is a collection of pairwise disjoint simple closed curves. So they are not necessarily a Pancy composition, but you can extend it to a Pancy composition. A Pancy composition, one way of defining it was a maximal collection of curves like that. So let me call it P. Now it's going to be alpha 1, alpha P, and then I'll go to alpha 3G minus 3. And what Minsky can tell us is the fact that essentially what the metric looks like on this subspace. So we look at the map phi that goes from this subset into the Teichmüller space of the surface where I removed these curves. And then I look at the product of hyperbolic planes. So I think of that as in the coordinates given by the Pancy composition. I have LITI. What do I do is, so if the curve is not one of the curves, I just use these coordinates to define the surface. So these are the LITI for I between P plus 1 and 3G minus 3. And then this is the product of TI 1 over Li for I between 1 and P. Okay, so I have a map here, and what Minsky tells us is that this is not far from being an isometry. Okay, let me see what I want to do. No, I'm actually going to leave it there. And go to another side. Yeah. Yeah, I won't be able to talk about boundary, but I will. It was a bit too much to hope for. Yes, yes. Yeah, so that's different from just before. And so we are all there using different models. I'm using the upper half space model. Barbara is using the Poincaré disk. And then there's the Klein model for Fanny. So we hope that someone else will use the hyperboloid model so that we are done. Well, at least, I don't know, maybe there's some other model that people use, but those have. Okay, then what he shows is that then there exists some constant t such that if I take any 2 point in this thin part, I can look at how much. So here I have a distance, here I have the hyperbolic distance, here I have the distance, the Teichmüller distance. And what I'm saying is that this map is not far from being an isometry. So the distance of the images minus the Teichmüller distance of the points themselves is at most d. So here, this distance here comes from the Teichmüller distance here, and here every time it's just a hyperbolic distance. Okay, so why this tells us that things are not hyperbolic? Because if P is at least 2, then a product of two H2s will contain a flat. And so what this is telling me is that in this thin part of moduli space, the metric is essentially something times something that contains a flat. So this metric is essentially, will contain, this space will contain flats. So there's no way that this space is hyperbolic. Yes?
I wonder what the constant B kind of...
It certainly depends on the, so I don't know precisely, but I mean, there's curves here. I don't know which curves I'm taking. I don't know how small this constant is. And I also just have the surface. I don't know whether it can be optimized in any sense, whether it can be made explicit, that I don't know.
So is that any kind of the choice of composition?
No, for the Pansy composition, I don't think it matters. But it certainly depends on the curves you've chosen. So that influences the Pansy composition you choose. Okay, and maybe I wanted to tell you, okay, not all is lost. This is actually really the lack of hyperbolicity in the sense that if you crash down these parts, you do get something that's hyperbolic. And this is Mazur and Minsky. Here I'm going to be very vague. So if we crash these thin parts into 2 points, so there's a way of making this precise, then we do actually get a hyperbolic space. And for those who know, this is actually a space that's quasi-symmetric to a graph, which is called the curved graph. Yeah, I certainly don't have the time to tell that. Maybe, okay, let me say. One thing is a very nice result by Wolpert. I don't know. Which gives you more of a, maybe of a geometric intuition about this distance. This links points at a certain distance with how the lengths of curves change. So if I have a map, which is K quasi-conformal between two hyperbolic surfaces, and I pick a curve on X, then I can look, this is not entirely defined, but I hope you see what I mean. I can look at the curve, how the length of A changes. So I take its image on Y, I have the length of this curve on Y, and I can try to compare it to the length of A on X. And what Wolpert tells us is that there's bounds that depend only on this K quasi-conformal, this quasi-conformal dilatation. So this is at most K times the length of A on X, and this is at least 1 over K this distance. So this tells me that if I have two surfaces, so if two surfaces have very small Teichmüller distance, and I pick a curve, that curve on one surface and on the other, and I take the geodesic representative on one surface and on the other, their lengths are multiplicatively close to each other. The ratio is the ratio between the two is small. And this is very useful when you actually want to use consequences of quasi-conformality, or if you want to show that something is not quasi-conformal. Well, we can certainly approximate it if you, well, it also depends what you have. There are ways of constructing metrics by looking at ratios of length. It does not give you exactly the same thing, but there's relations between the two distances, which is essentially given by this one. Yeah. But I don't think you can actually compute the type. Well, I mean, I don't think you can actually compute the k just by looking at lengths of curves. Okay, I have a couple of minutes, and I'm just going to say something for people who know what the boundary of Teichmüller space is. Let me tell one thing is, maybe what you want to say is there's a way of compactifying Teichmüller space by using what are called projective measured, what did I want, foliation or laminations? I wrote both. It's what you prefer, let's say foliations. So maybe what I can say is there is a way of constructing a boundary which turns this space, if you add the boundary, the space becomes a closed ball. So the boundary is a sphere of the right dimension, so that if you add it onto the Teichmüller space, you get a closed ball, which is very useful for many reasons. So this is, in fact, is that there exists a boundary. So one can define a boundary of Teichmüller space called the Thurston boundary, which can be identified with the projective measured foliations. And then with this, Teichmüller space, the closure of, meaning this union the boundary, is topologically a ball of the right dimension. And the last result I wanted to mention is the fact that so you can construct geodesics for this metric, and you can try to see what happens to these geodesics going at infinity. And the main point is they behave badly. It's a theorem of Lenton that there exists Teichmüller rays, so Teichmüller geodesics. And it's geodesic rays for dt. Which don't have a limit in this boundary. So they accumulate onto like they can accumulate onto a big set. And so there's a very naturally defined metric, and there's a very naturally defined boundary, but unfortunately they don't they don't talk to each other as much as they should. yeah, talking about the boundary would need another hour, so I'll stop here.